First off, I hope everyone in our audience is keeping in good health and staying safe. And I want to thank you for joining us in today's session as we talk about a transformative technology in the alkylation space, and that is Ionikylation. Just a brief overview of Well Resources and what we do. Well is a 100% Canadian-owned company operating out of Alberta, Canada, with satellites in Vancouver, Beijing, Guangzhou, and Qingdao, China. We focus on the development and process licensing of green, clean, and safe technologies in the petroleum sector, and our primary intent is to help our clients move the needle when it comes to adopting processes that benefit health, safety, and the environment. Increasingly, companies, investors, and society at large are demanding that we move towards more socially and environmentally responsible ways of doing things, and certainly our Ionikylation technology will play a vital role in that energy transformation. With that said, Ionikylation is just one of the technologies in Well's portfolio. Another one of our commercially proven technologies is the selective extraction of asphaltenes technology, or SELEX. This process is used to cleanly remove the asphaltene portion from resid in the form of solid granules, which can then be used for a variety of non-combustion purposes. To learn more, please visit wellresources.ca or reach out to a member of our team who will be happy to answer your questions. So on to our agenda. My objective today is to provide you with an overview of the Ionikylation technology and to give you insight into commercial operations. The presentation contains 4 subsections, with the first being an overview of alkylation, followed by a discussion on Ionikylation and our path to commercialization. I'll then share some commercial plant data before we wrap things up with a Q&A session at the end, time permitting. So notwithstanding the short-term impact of COVID-19, there has been a growing demand for alkylate gasoline, underpinned by an increasing consumer base and a move towards higher performance engines, which require premium fuels. In North America, there have been historical environmental concerns over alternative gasoline blending stocks, such as tetraethyl lead and MTBE, which contributed to air, soil, and water contamination. Stemming from this are changes from a regulatory standpoint relating to increasing fuel standards with the aim of getting better fuel economy and cutting harmful emissions. Alkylate is becoming increasingly sought after as a gasoline blending stock due to its inherently high octane number, typically in the range of 92 to 96 and as high as 98. Alkylate is clean burning, being free from olefins and aromatics, has low sulfur content, and is suitable for engines with high compression ratios, meaning more efficiency, more power for less fuel consumed. Here's a listing of the various options available for producing alkylate. The first group are what I would call the legacy alkylation technologies, which either use HF or concentrated sulfuric acid as catalysts. While both of these processes are well defined and widely implemented, refiners using acid-based alkylation technologies require exotic metallurgies for process equipment and costly safety systems to protect refinery personnel and the public. The disposal and regeneration of spent catalysts are also problematic. For example, regenerating large quantities of sulfuric acid is carbon and sulfur emissions intensive and bad for the environment. The second group are what encompass what I call the newer alkylation technologies, which include the use of solid acids and ionic liquids. A subset of the ionic liquid category is composite ionic liquid, or what I call CIL, and this is the basis for Well's technology. I specifically highlight the composite nature of our catalyst because it is the key to allowing us to overcome the typical corrosion and product selectivity issues arriving from non-composite formulations. Just to contextualize the risks associated with acid-based systems, there are about 50 refineries in the United States using HF, and on average, each facility stores about 212,000 pounds of this material. The EPA rates HF as highly toxic, and a large vulnerable zone must be established wherever this material is used. If released, HF tends to form a dense vapor cloud that can cause permanent injuries to the extremities and biological internals, and this has been widely explored already. So when things go wrong in a refinery, it can be devastating, and here are just 2 examples. In 2015 and 2018, incidents in California and Wisconsin presented very real near-miss scenarios for HF release, when units adjacent to the refinery alkylation units exploded. In both instances, nearby community members were forced to evacuate for their own safety, and these incidents really highlighted the risk of industrial-scale HF use near populated areas. Subsequently, local communities rallied to call for ending the use of this chemical in the operations and have even asked local regulators to step in. Some of our viewers might remember this. In mid-2019, there was a refinery explosion in Pennsylvania where the HF alkylation unit suffered a catastrophic failure. The end result was that the refinery was rendered inoperable, and the operator subsequently filed for bankruptcy protection. When we look at the bigger picture, over the years, there have been many instances of refinery personnel suffering injury as a result of accidental exposure to acid catalysts, irrespective of a catastrophic failure. Discussions on safety have largely been around preventative and secondary containment measures, largely due to the fact that there was no viable alternative, that is until now. But regardless of the safety measures put into place, there are real costs associated with the use of inherently unsafe processes in your operations, which can affect your bottom line. Here's just a sample from a Reuters article from January discussing the rising costs of insurance for refiners. In some cases, insurance rates have increased by 25 to 100%, and some refineries have subsequently pared back their coverage as a result. So let's talk about Ionikylation. This technology derives its name from composite ionic liquid catalyzed alkylation. Ionikylation is characterized by 5 sub-processes. The first is feed pretreatment, followed by reaction, then product separation, product treatment, and catalyst regeneration. And here we show the simplified flow diagram for the process. Mixed olefin feedstock is first pre-treated to remove contaminants such as water, sulfur, and oxygenates. In the Ionikylation reactor, the feed is mixed with a dense, circulating, continuous phase homogeneous CIL catalyst to facilitate the alkylation reaction. Reactor effluents are then routed through a series of settlers and separators that differentiate the alkylate and other light ends from the high-density catalyst. Alkylate and light ends are subsequently subjected to fractionation, and unconverted reagents such as isobutane and N-butane are collected and recycled as needed. Depending on the user's required product specifications, alkylate may be subjected to a variety of post-treatment methods such as chloride removal, typically by adsorption. At the bottom, extraction is used to remove a small quantity of spent catalyst from the process in the form of a benign solid, while the recovered catalyst is routed to the catalyst regeneration unit. At the catalyst regeneration unit, makeup catalyst active reagents are introduced. A regenerated catalyst is then routed back to the Ionikylation reactor, and an organic chloride compound is added to supplement the catalyst activity. So there are many advantages to the Ionikylation technology, and as I said previously, at WELL, we're really looking to move the needle and provide a stepwise improvement to the current way of doing things. We understand that to do this, any compelling technology has to be competitive from a process performance standpoint, as well as from an economic standpoint. By far, the greatest advantage of Ionikylation is its ability to eliminate a refiner's reliance on toxic and corrosive acid catalysts such as HF and sulfuric acid, which increases the safety for refinery personnel and the public. Because of the non-corrosive nature of our catalyst, all Ionikylation process equipment is manufactured using carbon steel, which significantly lowers the capital cost burden for greenfield and brownfield new builds, as well as revamp and replacement scenarios. Our catalyst is also formulated to have high selectivity towards producing the most valuable high-octane gasoline constituents, such as trimethylpentanes, while limiting the production of undesirable byproducts, such as acid-soluble oil or ASO. Our process also includes an on-site catalyst regeneration unit operating under moderate conditions, which significantly reduces emissions when compared to a scenario where you have to truck large volumes of spent acid catalyst to an off-site facility for treatment. When we compare the legacy acid-based alkylation technologies to Ionikylation, a very clear picture forms. With HF, indeed, it is among the best in terms of producing high-quality alkylate due to its high activity and selectivity. However, it ranks quite low on safety measures as it's both hazardous and extremely corrosive. In comparison, while sulfuric acid is less hazardous, it still makes for a corrosive system, and catalyst activity and selectivity measures are greatly diminished. Hence, why sulfuric acid-based alkylation systems require orders of magnitude more catalyst than the others. For our CIL-based process, it simply checks off all the boxes in terms of safety and performance, and I'll get into more of this as we progress through the presentation. Here we summarize the typical ranges of operating parameters for the key pieces of ionikylation equipment. And as you can see, the conditions are quite moderate. We normally recommend a feed isobutane to olefin ratio of 8 to 10 to 1, but it is not unheard of to have specifications outside of that range, which we can look at for you on a case-by-case basis if needed. When feed is injected to the ionikylation reactor, the reaction happens quite quickly, and in the presence of excess isobutane, we observe an isobutane to olefin ratio inside the reactor of greater than 100 to 1. From a process performance standpoint, ionikylation produces superior quality alkylate with octane numbers ranging from 96 to 98, and this is dependent on the feed quality as well as how the user operates their unit. A very small amount of ASO is produced in the process, accounting for less than 0.1% of alkylate produced, and it is recovered and typically used as a diesel hydrotreater feed. Ionikylation is the culmination of over 20 years of research and development, and not only is it now market ready, it is already implemented in Asia with demonstrated through multiple commercial units. Catalyst and process development started in 1998, and it took a few years for us to formulate, synthesize, and fine-tune the details. In 2003, we successfully completed a 2-month, 20 tons per year or 2 kilogram per hour continuous pilot test. And in 2005, we were given the opportunity to retrofit a commercial scale sulfuric acid alkylation unit owned by PetroChina, which yielded promising results. In 2013, the world's first greenfield ionikylation unit was commissioned in Shandong, China. And this was built and operated by a private company as a standalone boutique unit supplying alkylate to the local market. Commercial licensing ramped up in 2017 as Asian refiners began prioritizing health, safety, and environment in their operations, supplemented by that 2013 unit demonstrating commercial viability. In 2018, 6 additional units were licensed, and PetroChina commissioned its first ionikylation unit at its Harbin refinery. In 2019, 2 additional units were commissioned, one by PetroChina and one by Sinopec. And Sinopec also commissioned its second unit in the first quarter of this year at its Wuhan refinery, which was the world's first revamp from an existing HF unit. Very briefly, I'm just going to dive a little bit deeper into this red highlighted portion of the timeline, as it provides some very important context for why CIL is differentiated from other ionic liquids. So back in the late 1990s, we originally explored the use of ionic liquids as a quote-unquote super acid catalyst to crack petroleum residua at low temperatures. And while we were largely unsuccessful in that endeavor, we did find that CIL was an excellent alkylation catalyst due to its high activity and reactivity and selectivity towards producing high-quality alkylates. But to get there, it was a bit of a journey, and there was a lot of trial and error in between. So here in the red, we show the iterations that represent our first trial stages, where we aim to modify product yield and selectivity. We found that this could be achieved by modifying aluminum chloride mole fraction, as well as doping the ionic liquid with acids such as HCl. Unfortunately, these systems we found were still corrosive, and our thinking at the time was that if corrosion still persists, that is not much of a stepwise change from the existing acid-based systems. So next, in the yellow, are the second trial stages. Here we tinkered with different formulations to overcome the corrosion issue while maintaining activity. But what we found was that these mixtures tended to produce suspensions with the alkylate, which would make it difficult to separate in commercial settings and therefore non-viable. Last, our team was finally able to develop an optimal CIL catalyst that could overcome all of the issues mentioned previously, in that it produced what we wanted, it was non-corrosive, and could be easily separated from the alkylate product. This table summarizes the 6 commercial units constructed or already commissioned in Asia. 5 additional licensed units are either at the engineering stage or under construction, with the largest one currently slated with a 400,000 tons per year processing capacity, or roughly 10,000 barrels per day. So in total, worldwide, there are currently 11 commercial ionikylation licenses issued. Here are just some photos of the constructed units. On the left is the 100,000 tons per year standalone ionikylation unit from 2013, owned by independent refiner Deoyan Chemical Company. Plant data from this operation has been published in the March 2018 issue of Hydrocarbon Processing, and I encourage the viewers in the audience to check out that as an additional reference point. On the right is the 150,000 tons per year brownfield ionikylation unit owned by PetroChina, commissioned in 2018. Here are the images from the ionikylation units commissioned last year by PetroChina and Sinopec. And here are the Sinopec units with 2020 commissioning dates. The Sinopec Wuhan unit shown on the left, as previously mentioned, is the world's first commercial scale revamp from an HF alkylation process, and we're very excited about that. This revamped unit was one of the last 2 remaining HF alkylation processes in operation in China. The Sinopec Anqing unit shown on the right was originally scheduled to be commissioned earlier this year, but due to complications from the COVID-19 pandemic, the scheduling has been pushed out to later this year. So the next section is a case study of commercial ionikylation performance from one of the recently commissioned units in Asia. Specifically, the data comes from the PetroChina Harbin unit that was commissioned in November 2018. At this point, I do want to thank PetroChina Harbin for allowing us to share this data in a public forum. After about half a year after commissioning, the operator conducted a calibration test to benchmark and compare commercial performance data against design specs to identify optimization opportunities. To date, no safety-related incidents or concerns have been identified. And for anyone receiving a copy of this presentation afterwards, the equipment list provided on this slide coincides with the diagram over here on the next. The process operating flexibility for the Harbin unit was 60 to 110% of the designed processing capacity, and feedstock originated from an upstream MTBE unit. For this operation, a feed pretreatment hydrogenation unit was required for the hydrogenation of methyl ethyl ketone, and a dechlorinating adsorption agent was used for product treatment. This table compares the commercial process operating parameters for key equipment against the design parameters. The operating temperatures for the alkylation reactor were about 10 to 15 degrees higher than the design values, but nonetheless, they were quite moderate in the grand scheme of things. As you can see, the alkylation reaction is slightly exothermic. Oftentimes, we'll be asked about the impact of operating the alkylation reactor at a higher or lower temperature. And based on our experience, for every about 10-degree increase in reaction temperature, this will decrease your alkylate octane number by about 1. Where this comes into play is during the design phase of a unit, where feed quality and an operator's product octane requirements will guide us in determining the degree of cooling that is needed in your system. Here we show a comparison of the commercial and design feed compositions. Our customers often look for comparable data points to give them an estimate of what quality alkylate can be expected from their feedstocks. And while we now have multiple commercial data points that we can reference, I also do want to point out that Well Resources has the capacity to perform custom feed pilot testing if required. One takeaway from this table is that regardless of what you design for, commercial operations are often difficult to predict and will always observe some degree of deviation. But despite the highlighted deviations in feedstock, composition, and reaction temperature, our process still rises to the occasion. Here you can see that ionikylation meets or exceeds key product specifications, such as octane number and vapor pressure, and this really speaks to the robustness of our process. Also, the low alkylate chloride content shown at the bottom of this table indicates that product treatment dechlorinating agent chosen for this operation was highly effective. Here's a more detailed breakdown of the alkylate composition. The process achieved 100% olefins conversion, and the vast majority of the product stream consisted of the sought-after isoalkanes. The C8 alkylate yield was about 77%, which is comparable to or exceeds the performance of traditional acid-based alkylation processes. Utilities consumption is also provided on a normalized basis in a kilogram of oil equivalent standard. And the takeaway here was that the commercial operation fell within 1.5% of the design specs. Note that the utilities consumption load for our process is quite similar to the traditional acid-based systems. Since ionikylation is a catalyst-based process, it's only fair to talk about catalyst consumption. For this operation, the design catalyst consumption was based on the performance of the previous commercial unit commission in 2013. However, due to recent process and catalyst manufacturing improvements, total catalyst consumables for this Harbin unit decreased by 46%, leading to increased significant, immediately realized and ongoing cost savings for the operator. One thing I also want to emphasize is that ionikylation is still a relatively new process, but this means that there's a lot of opportunity for improvement as the process becomes more widely adopted into the future. The spent catalyst byproduct from our process is chemically benign and can be safely handled and disposed. Here you can see the various stages of byproduct handling, moving from a benign paste discharged from the process all the way to a dry mineral-like solid. A relatively small amount of this material is produced, and based on existing operations, it can be removed every few days up to 2 weeks, depending on the operator's needs or preference. Disposal options are also dependent on an operator's philosophy and local regulatory requirements, if applicable. This is just a brief reference to that 2013 Greenfield unit constructed by Deyan Chemical Company. The crux of our process is the use of the non-corrosive CIL catalyst, which allows for all process equipment to be manufactured using low-cost carbon steel. This Deyan unit operated for 3 years continuously before it was briefly shut down for a 2-week period for a rigorous government safety inspection. The inspection found no signs of corrosion within the process equipment whatsoever. There were no mechanical or maintenance issues, and the operator had no problem restarting the unit. So in terms of ease of operability during a turnaround scenario, we don't see any issues. And with regard to the frequency of turnaround, all I can say is that the most likely scenario for taking this type of unit offline would be when performing a turnaround on units upstream of the process where you disrupt the feed. Here is the recommended guidance for feed contaminant limitations. And the takeaway here is that there are various control measures available for achieving these specifications. We do very tightly want to control water content in the feed because it will hydrolyze the CIL catalyst and break it down. And as a feed pretreatment step, we also frequently recommend isomerization of 1-butene to 2-butene, as this will drastically improve the alkylate product octane number. Greater degrees of other contaminants typically serve to reduce the catalyst activity, which means you might need more catalyst if contaminants are not controlled. Lastly, I want to just quickly discuss scenarios for converting existing acid-based alkylation processes to ionikylation based on our previous experience. Regardless of which process you're converting from, the minimum equipment required will include the ionikylation reactor and the catalyst regeneration system, as they're unique to our process. In addition, depending on the integrity and setup of your existing equipment, a new product fractionator may or may not be required. For revamping a sulfuric acid system, much of the existing cooling system may be reused, but for revamping an HF alkylation system, which typically doesn't have additional cooling, a refrigeration system might be a consideration depending on the end user's alkylate quality requirements. In any case, each conversion scenario is considered on a case-by-case basis. So in conclusion, a safe, sustainable, and viable alkylation alternative now exists, as commercially demonstrated in both greenfield and brownfield operations. That technology as well as Ionikylation technology, and we see it as replacing the traditional HF or sulfuric acid-based systems that are unsafe and harmful to the environment. Ionikylation is cost-effective, safe, and environmentally friendly. It uses a non-hazardous and non-corrosive catalyst that allows for all equipment to be manufactured using carbon steel. It also has high activity and selectivity towards manufacturing the most valuable alkylates and will meet the needs of a green and clean energy future. With that said, I want to thank you for joining us today. To learn more, please visit wellresources.ca or reach out to a member of our team, and we'd be happy to answer any of your questions. Thank you.